Here's a game with only 2 rules. Pick any whole number. If it is even, halve it. If it is odd, triple it and add 1, then do it again. That is the entire game. Start with 6. 6 is even, so halve it and we get 3. 3 is odd, so triple it and add 1 and we get 10, then 5, then 16, then 8, 4, 2, 1, 8 steps and we have arrived at 1. Now do not stop. 1 is odd, triple it and add 1 and we get 4. Halve it 2, halve it 1, 4, 2, 1. 4, 2, 1, forever. Once you touch 1, you are trapped in a loop of 3 numbers. 6 was gentle, try 7. 7 is odd, so it jumps up to 22, then 11, then 34, then 17, then 52. It climbs to more than 7 times where it started, but 16 steps later it lands on 1 and falls into the same loop. Now the strange part, take 26, 10 steps to 1. Its neighbor 27 is 1 larger. Same rules, same size. 27 takes 111 steps, and it does not stay small on the way. It climbs to 9,232, 342 times where it began. Then it comes all the way back down to 1 and into 4, 2, 1. Every number anyone has ever tested does this. Now one piece of notation. Call the rule capital T. T of n equals n over 2 when n is even and 3n plus 1 when n is odd. One line and it holds the whole problem. Test it on the number we did by hand. T of 6 is 3, T of 3 is 10. The same trajectory. Now the notation shows us something the numbers hid. If n is odd, then 3n is odd and 3n plus 1 is even. So an odd step is always followed by a halving. Always. So pair them up. From an odd number you really go to 3n plus 1 over 2, about 1.5 times as big. But sometimes you have twice. Or 3 times. On average you have twice. 3 divided by 4. 0.75. On average, odd numbers get smaller. On average is not always. An average describes what usually happens. A conjecture has to be true for every number with no exceptions ever. And there are exactly 2 ways this one could fail. 1. Some number could climb forever and never come back down. 2. Some number could fall into a different loop. A loop that never passes through 1. Nobody has ruled out either. And numbers really do climb. Take 837,799. It is smaller than 1,000,000. It rises to almost 3 billion, 3,500 times where it started. It needs 524 steps to come home. It does come home, but nothing in the rules promised that. We only watched it happen. So why can nobody prove it? Here is the cleanest reason. Change one symbol. Keep triplet but subtract 1 instead of adding 1. Everything else identical. Start at 5. 5 is odd, so triple and subtract 1. 14 have 7, triple and subtract 1. 20 have 10, have 5. We are back at 5. That is a second loop and it is real. So there is no deep structural reason forbidding other loops. The plus 1 is doing all the work and nobody knows how. What has been proven is narrow but sharp. Any other loop would have to contain more than 100 billion odd numbers. And in 2019, Terence Tao showed that almost every starting number eventually gets very small. Almost every, not every. This problem is 90 years old. In 1937, a young German mathematician named Lothar Collatz wrote it in a notebook. He never published it. He told people instead. At the 1950 International Congress of Mathematicians, he mentioned it to Kakutani, to Ulam, to Coxeter. In 1952, he moved to Hamburg and told Helmut Hasse. Hasse carried it to Syracuse University, so it spread by word of mouth, and it collected names as it went. The 3n plus 1 problem, Ulam's conjecture, Kakutani's problem, Hasse's algorithm, the Syracuse problem. Paul Erdős offered $500 for a solution and said something that stuck. Mathematics is not yet ready for such problems. Computers have now checked every number below 2 to the 71st power. More than 2 sextillion of them. All of them reach 1. None of this is a trick and none of it is a paradox. Every step in this video is arithmetic a child can do. That is the point. The rules are 2 lines. The question is 1 line, and 90 years of mathematics has not closed it. 3 things to keep. First, the loop is real. 4, 2, 1 forever for every number anyone has ever checked. Second, the reason we believe it is a drift. 3/4 on average at every odd step. Third, a drift is not a proof. Change +1 to -1 and a second loop appears. Halve it or triple it and add 1. Nobody knows why that always ends at 1.